Good morning, everybody. Today we're going to look just a little bit at your last contact force. We've already looked at applied forces, which you have to use the concepts to find. There's no particular equation for an applied force. We have looked at normal force from a surface, and that also has to be found using the concepts. Friction we've looked at. It has its own formula, although you can find it using the concepts as well. And now we're going to look at tension force, okay? So here we go. Tension force. Now, in the past, a lot of scientists have used a capital F sub T, but today a lot of physicists just use a capital T to represent tension, kind of like we use a capital N to represent normal force, okay? And just like all forces, it's measured in the Newton. Now, tension force is a force exerted through a wire, rope, string, cable, tether, whatever you want to call it, thread, anything that you can that is flexible that you can use to pull. And one thing you have to note about tension is that it always points away from the object being pulled. In other words, tensions cannot push, okay? Now, some people would argue that you could look at the tension in a spring. Well, yeah, you could, but we usually call that spring force, and it's a little different than a tension in a wire or a cable. So here I have a string tied to this ball. Notice if I try to push it, it doesn't do much. But if I pull, it certainly does a lot better job, doesn't it? Okay. So now, where tension is concerned, again, like applied forces and normal forces, there is no one particular equation like there is for friction and gravity by which you can find a tension. You have to use your concepts of equilibrium and non-equilibrium to find an unknown tension. And we're going to do that in a minute as soon as we do talk about a few things where tension is concerned. There are two terms I want you to be aware of where tension is concerned. They're not on here, so we're going to put them on here. The first term is the term slack. Okay, slack. When you have a slack tension, that simply means there's not a lot of tension in it. Like right now, this string is slack. There's very little, if any, tension in it being exerted on the ball. Okay, and if I pull, however, then the string gets very straight, and you can tell that I'm pulling with it. In such a case, we say that the string is taut, T-A-U-T, taut. So slack and taut. Those are two terms you need to be aware of because that's one of the things. Those are two of the terms that we use to describe the string when there's a little tension or very little tension or a lot of tension. Okay, so slack, only a little tension. Okay. Small t, if any, and taut means a large T. Okay? Now, some other things I want you to be aware of, and we're going to do a few little diagrams. You don't necessarily have to put this down, but you might find it useful if you've got a little scrap paper somewhere. You can always pause this video to get one if you want. Let's look at a few situations for things we need to know about tension. Let's start by looking at an object that is hanging from a thread. Okay, in a case like this, if the object is hanging from a string, it is at rest, so you're in equilibrium. In which case, the tension exerted by the string and the weight of the mass must balance because you're at rest. You're in equilibrium, okay? Now let's look at a slightly different situation, and this is one that's going to look somewhat familiar to you, okay? If we have two strings pulling up to either side at the same angle. Okay, in a case like this, if the two strings are at the same angle theta, then they are equal. Each one supports half the weight. So you'd have two tensions drawn the same length, and they're supporting, their vertical components are supporting the weight of the object. Okay, so here we could say, in this case, we could say, let's see, the vertical component is adjacent to the angle, so we could say 2t cosine theta equals mg. Okay, because we have two vertical components, and together, well, if we look at it this way, over and up, the two vertical components together balance the weight. So 2t cosine theta equals mg. All right, so each one supports half the weight. But now, if they are at odd angles, like this, the one that is more vertical will actually have the greater tension. So if we label these T1 and T2, in this case, all right, T2 would have to be greater than T1. It's more vertical, so it will have the larger vertical component and therefore support more of the weight. In fact, in this case, we would have to say T1, if these are the theta 1, theta 2, just keep your subscripts together, T1 cosine theta 1 plus T2 cosine theta 2 equals mg. All right, so for conditions of equilibrium, that would be true there. I'm sorry if you couldn't see that. There we go. All right, so that's kind of how it works in a situation such as that. Let's look at something else, though. Let me turn this over. Beep. Okay. What if we had a string that passes over a pulley? Okay. Maybe it's tied to a box and it passes over a pulley. You've got we're going to see a lot of these, by the way. And you've got a mass right there. Okay, we want to know, what about the tension in the string? If this box is at rest, or maybe moving at constant velocity across the table, all right, toward this way, then we know that the system is in equilibrium. But we'll look at that later. What I want to look at now is the tension in the string. So let's look at the tension here and versus the tension here. What is it going to be? Well, if this block is at rest or constant speed, then we know that right here, mg equals the tension, and the tension is pulling up. Now, it's also pulling this way on this block. All right, so what happens? Well, basically, all you're doing as the tension, well, it's pulling this way on this block, but you could still look at it as pulling this way from that block. So let's just look at that little block. Let's not worry about that one. Okay, so all the pulley does is change the direction of the tension. That's it. That's what a pulley does. It changes the direction of a tension. So basically, the tension at point A and point B are the same. The tension at those 2 points are the same because it's the same string, so they have to be the same. You cannot have a single string with 2 different tensions in it, okay? You just can't do that. So the pulley changes the direction of the tension so that it is acted on the other box too. Now, let's see. Let's try a different situation. Let me think of one here. Oh, okay, how about this one? You're going to see some of these. All right, and we've got 2 pulleys this time. And we want to know what is the tension right there. Okay, let's suppose this is 60 newtons and this is 60 newtons. Okay, so what would be the tension at point A? Well, it would not be 120 newtons. This mass pulls on this one with a weight of 60 newtons. So the tension in the string for this mass is 60 newtons. But since this mass also weighs 60 newtons, the reaction force is it pulls on that one with a force of 60 newtons, and they stay at rest. Okay? So right here at this point, the force or tension in the string is 60 newtons. All right? It pulls upwards on this one and upwards on this one. Think about it. If the force were anything but 60 newtons, the system would have to accelerate, but it doesn't. So the tension has to be 60 newtons. If you have blocks being pulled, okay, and you've got T1 and T2, which of these 2 strings has this greater tension, or are they the same? Well, if the system is moving to the right or to the left at constant velocity, what do you think is going to happen? Well, think about it. This tension has to pull 2 masses, not 1. This tension has to only pull 1 mass. All right? So the 2 tensions in this case, this one has to be greater than this one only because it has to keep both masses in motion. This one only has to keep 1. If the system is accelerating, it's still going to be the same according to Newton's second law. To accelerate 2 masses, this tension has to be greater than this one because this one only has to pull 1 mass. So that's kind of interesting too. And at the moment, I can't think of any more little situations that you might come up against. Of course, on the AP exam, they love giving you all sorts of weird stuff. But those are pretty inclusive right there. And most questions can be answered by what we've just looked at. So now let's go back to our notes. And let's take a look at this example right here. Okay? On this example, it says, determine the tension that would have to act on a 5 kilogram block to keep it sliding at constant speed, so we're going to be in a condition of equilibrium, along a horizontal surface where the coefficient of kinetic friction is 0.75. So we're given the roughness between the surfaces, and we know the mass of the block. So we have that we're in equilibrium because V is constant. We know that. We know the mass is 5 kilograms. We know the coefficient of kinetic friction is 0.75. Notice the block is already moving. We don't have to worry about overcoming static. Okay? So let's see. We want to know the tension. All right, so let's make a free body diagram. There is the surface that the block is sliding on, and there's a dot to represent the block. And let's assume that the block is sliding to the right. I just like doing it that way. If you want your block to slide to the left, that's fine. You're just going to mirror image your picture. So we have a tension force. Let's use a different color. We have a tension force right here that is acting on the block to keep it moving at constant velocity. And it is opposing the friction, which points the opposite direction. And this is kinetic friction. Then we have normal force from the table, and we have the weight of the block, mg. All right, now, what do we know about this situation, about these forces, if we're in a state of equilibrium? Okay, we know 2 things have to be true. Number 1, the tension must balance the kinetic friction. And number 2, the normal force must balance the gravity. Those two things have to be true since it's staying on the surface of the table. This plane has to balance, and since it's moving at constant velocity in this plane, these two have to balance. Okay, so we're in equilibrium in both planes. Now, we want to find the tension. Well, we just said the tension is equal in magnitude to the kinetic friction. So let's write that. Let's start with that. All right, and we know how to find kinetic friction. It's mu k times the normal force pressing the surfaces together. Notice I'm only using magnitudes. I don't care about directions right now because we're not adding or subtracting anything. This is all multiplication. So now the normal force we don't know, but we do know it's equivalent to the weight. So I can substitute mg in for that. Now remember, that's only on a horizontal surface I can do that, all right? If the surface is vertical or on an incline, I cannot say N equals mg. So don't get it in your head that the normal force is always mg. It is not always mg. Be careful. Don't fall into the trap. Okay, we know mu k, we know m, we know g, so now we can find the tension. We just substitute. So 0.75 for the coefficient times the mass times the acceleration in free fall. Okay, and if you stick that in your calculators, I do believe that you get 36.8 newtons. Boom. How about that? That wasn't so tough, was it? Okay, so the next few days we are going to be working with tension, and then we're going to start bringing everything together. Okay, all of our forces, what happens in non-equilibrium situations, which we haven't talked too much about yet. We've mostly been using equilibrium, maybe a little non-equilibrium once in a while. Oops, there's the bell. And let's let it finish. There we go. And we'll be looking at a lot of different situations, bringing it all together to see how we can determine unknown quantities for various situations, okay? So, thanks for listening, and I'll see you guys on Monday. Bye-bye.